Hello, welcome. Welcome to 537 installment, what? Three? Part three. All right. Trilogy. Unfortunately, it's a 14 episode movie. And like I said, it doesn't get any better. So, what we're going to do today is get back into the swing of things. We're going to essentially finish our discussion of CPU virtualization. We've talked so far about mechanisms, the ability to switch between processes so that we can implement a scheduling policy, the ability to regain control of the CPU by having a timer interrupt, and all of this was under this general idea of how to build virtualization, which we called limited direct execution, or I'll just call it LDE for short. Direct execution, because most of the time what we're wishing for is to just, when we want to run a user program, we just want to let it run. And the hardware is fast, and if we want things to happen quickly, we don't want the OS to get in the way. But limited because we're going to add mechanisms, or we did add mechanisms, to the hardware as well as to the OS in order to allow us to make sure that user programs don't take over the system and don't hurt each other in any way. So we're going to finish that discussion today because last time what we started to do is we start to build up on top of these mechanisms by building some policies, deciding inside of what we might call the OS scheduler, basically this question of at a given moment, we want to know which process should run. Okay, that's a question we want to answer inside of an OS scheduler. I have the ability to decide, I want to run A, or I want to run B, or I want to run C, but the reality is I need a way of choosing and having some idea of how to do that. So that's what the scheduler is going to do, and what we're going to do today, what we saw last time what we saw was what we saw was some kind of an introduction to some things that are useful to us in building up a scheduling policy. So we saw a general notion of shortest job first, or SJF. Shortest job first was useful as a concept because if I have two things to do, and one I can accomplish quickly, and one takes a long time to accomplish, it's essentially better by some metric to do the shorter one first, because to the shorter job it makes a much bigger difference if it had to wait behind the longer job. If the longer job has to wait a little longer, it doesn't really affect it, but the shorter job, it matters a lot if it runs first or later. So that's a concept that we'll use. Now the problem with shortest job first is it assumes knowledge of runtime. And we generalize that a little bit to shortest time to completion first, but it's the same idea. So this is unrealistic because it assumes knowledge of runtime. We don't generally know how long processes are going to run for, and therefore we wouldn't even know how to implement a shortest job scheduling policy because we don't have that knowledge. And like I said last time, there are some environments where that's not true, but here we'll assume it is true. We then also saw a scheduling policy called round robin last time. Round robin, instead of running one job to completion and then the next, was frequently switching between different jobs. So instead of running A in its entirety and then say B afterwards, that's not round robin, not RR. What we would do is just run A for a little bit, then B, then A, then B, etc. We called each of these things maybe a time slice or a quantum. And of course, that's some multiple of the timer interrupt period of the system. So we're assuming a preemptive system that the timer interrupt goes off periodically and we might decide to run something else. And round robin would be maybe switching frequently between them at whatever the time slice that we decide on. So unlike shortest job first, this is what you might say it's super responsive, which is good for these kinds of interactive jobs where you want to kind of know that you're getting some CPU time right away. But then again, it kind of has the opposite behavior of shortest job first, is it stretches everybody out. Everybody gets stretched out in this round robin way, so they all finish a long time later. And so maybe that's not the greatest thing either. So what we're going to do today, sorry, I'll write that here. The first thing we're going to do today, and then we'll take a break after this, we're going to develop a real scheduling policy. This is based on what you would call kind of the classic Unix scheduler is where this came from. It still is in use in various systems. It's not in Linux. We'll talk about Linux maybe at the end, and we'll talk about Linux in a later project too, or project 2B actually. But it's a very influential scheduler, and like I said, used in a bunch of systems today, like Solaris, if that still kind of exists, or variants of Solaris, which still kind of exist. Windows, some variant of this exists. And some of the BSD systems as well. So we'll develop this real scheduling policy that doesn't make any of the assumptions that are unrealistic. For example, we won't assume that we know how long jobs run for. And we'll call this general approach a multi-level feedback queue. And that's a mouthful, but we'll just call it MLFQ for short. And that'll be a general principled approach to building an OS scheduler. So by the end of the next 40 minutes or so, we should have an understanding of that. But that's not all we're going to do today. So we're going to then finish up our discussion on CPU virtualization, remembering that the general idea with CPU virtualization is we're trying to make the system seem as if you have as many processors as you need, as many as you wish to run, and we're just sharing them among the many processes of the system. We're sharing a few physical resources. That's virtualization, and it's this beautiful thing that the OS does for us. But there's a big piece of it that we've missed, so later today we're going to start unmissing it, I guess. And what we're going to focus on later today is we're going to start to talk about the other part of the OS that really contributes to virtualization, which is virtual memory. We've been ignoring memory, essentially, for simplicity. We'll do that a lot in class. We will ignore something, we'll put our blinders on and pretend that that thing doesn't exist, and then we'll slowly open our eyes up to it so that we can understand the full system, because it's complicated. Systems are complicated, and if you try to understand it all at once, you kind of miss out on some things. So we try to do kind of piece by piece, and hopefully it'll make more sense then. Awkward gulp on the video. So that's what we'll do next, and then we'll just get into the details of that. We'll spend quite a bit of time on virtual memory, something you've been introduced to, I think, in 354, but we'll go a little bit deeper than that, and then at that point we'll kind of end the first part of class, which is the virtualization of CPU and memory, really in totality, and you should have a very good idea then, modulo the last two parts of class, about how a program is loaded into memory, runs, and shares CPU and memory among all the different systems in a safe and efficient way. And we'll see, of course, there, just like we saw with CPU virtualization, we'll see with memory we need even more hardware support to make it efficient and more OS support to make it protected, along with the hardware support. Okay, and then somewhere in the breaks, we'll talk about other parts of class. So that will happen. So that'll be the second part of today. And then the third part of today, so that's today, then later today, and then because we like suffering together, we have a third part of class which is called later today. Yeah, kind of mild laughter. And later today is unfortunately going to exist today. And what we're going to start talking about there is actually I'm going to start talking about, because we're almost done with Project 1B, let's start talking about Project 2A. So we'll do that, and that relates to processes, and actually a Unix shell is how you learn about that. So almost any OS class that you take, you're going to implement a Unix shell of some kind, some variant. So each time we go through the class, we add and delete some different features, and you go and build a shell. And once you build a shell, you not only understand the concept of CPU virtualization, but then you'll have used the APIs to create and control processes. So you'll understand the API side of it as well as how it's built internally. So something to look forward to later today. So as always, we're in for a long night, and then maybe, along the way, we'll try to do some fun things. Last week, we predicted the future. We'll revisit those in your 50th year reunion when you come back here in 50 years, and we'll have, we predicted 100 years out, so we won't be able to see that, but we'll come back in 50 years and look at those. Maybe we'll do some shorter term things at the breaks tonight that we'll talk about for a change of pace. As you can tell, I like being distracted from class. You think it's just you. I like it too. So anyway, it's fun to talk about class, and it's fun to talk about not class all in the same time. Okay, so why don't we get down to the work part. Always work is ahead of us. And like I've probably said, what is life but work? So life, work, these are the same things for us. You say, no, there's more to life. Is there? I don't know. That's a good question. Even like enjoying something like watching TV, sometimes it feels like work, right? You're like, you have to sit there, you have to eat something. It's a lot of work to watch TV. So anytime you think you're just enjoying yourself, you're actually working. Okay, so let's go back to part one, which is OS scheduling policy. And what we're going to try to do is build this multi-level feedback queue in order to build a real scheduling policy. We have a central problem that we must address in almost any OS policy. And we'll address it in one way over and over again because that's what we've been doing for many years inside the OS. Maybe that's changing. We'll talk about how that's changing right now, actually. But the problem is that we really don't know very much about jobs, about the running processes. That's not even a question mark. That's the wrong punctuation, exclamation point. We don't know much about processes, exclamation point, because users just type in something at the shell and it starts running, or whatever. Some servers inside of a Google data center are running different binaries from different cloud customers. What do we know about what their jobs are? Not very much. They just started running. So we need to figure out something. So we need, and what we'd like to learn, for example, is which are, for example, short jobs and which are maybe longer running. Because if we knew that, we would try to make those shorter jobs run quickly, and then everyone would be happy who's running a short job. And then the longer running jobs, that's okay. We'll just make sure we make progress on them so that they also are happy and they understand that the short jobs can run in front of them. So that's what we need to learn. So the question is how? How are we going to learn this? Well, what are some different ways we could learn this? Or know job runtime? What could we do? Yeah. Yeah. So one way to do it is kind of measure something. And what we're really doing then when we're measuring the existing behavior of jobs is we're essentially trying to say maybe we're using the past to predict the future. This is the basis of anything that learns. If you take a machine learning class, that's a different kind of learning, and obviously a much more sophisticated kind of learning. But here we're talking about a very simple kind of learning about these running processes, where we say, well, what have they been doing recently? And if maybe that's a thing that they were doing recently, we can learn something about that. So this is going to be our one general tool that we'll use almost in every policy that we look at. Like I said before, I don't think the policies are super complicated that we're looking at, but we just have to be methodical in how we approach building them. So that's going to be our goal. We could, of course, do other things too. If we wanted to know job runtimes, we could. What else could we do? If we just had an open slate, we wanted to know something about our running processes, what could we do? Nothing, apparently. We could do nothing. That's always a good option. Doing nothing is better than doing something bad. So. Okay, so sure. I mean, we can measure lots of different things. We could measure how long it's been running. We could measure aspects of what kind of program it is. We could measure, what else could we measure just about our running programs? Yeah. How many I/O calls it makes? Maybe I/O calls is giving some sense of, is it waiting on disk I/O a lot, or maybe it's waiting on the keyboard a lot. We can record things like the name of the process. Maybe we can do some machine learning on the name and say every time a program runs that's called, has a very short name, then it doesn't run for very long, and very long name processes run for a long time. That could be true. Who knows? In fact, maybe if you assume it's true, users will start encoding run length into the job length, the name of the job. Who knows? You could do all sorts of things. You could prompt the user even. You could tell the user, please tell me how long you think this job runs for, and I'm going to use that to schedule you. In fact, there are many systems, batch scheduling systems that ask you to estimate how long a job will run for, and they use that in scheduling. We're not going to assume any of these fancy things here. We're just going to observe simple things about runtime and see if we can do something better than just round robin, for example. Okay, so good thoughts. So let's start building the multi-level feedback queue. In order to understand this, we have to understand why it's called the multi-level feedback queues system. And it starts with having many queues. So instead of one scheduling queue, like a round robin queue, we have many queues. And we can have arbitrary many of these. I'm just going to draw 3 of them here because I don't like drawing more than 3. It's a fundamental reason. And we will see that these 3 queues are going to be, a job can be on any one queue at a time. So a job or process is on one queue at any given time, but this might change over time. Okay, so there are many queues, and jobs might be on the job can be on any one of them. Let's say A is on this queue, and then B and C are on this one, and job D is down on this queue. I will assign each queue a priority. So I'm going to give you a bunch of facts, and then we'll start to see the dynamics of how the system works. Has a notion of a priority. And if we're talking about priority, it's directly related to which queue it's on. So here, Q2 is the highest priority. This is the middle priority. And this is the low priority. Or in Starbucks terminology, this would be what? Tall, grande. What's the highest? Venti. Yes, venti. Why do they do that? I don't know. It's to sound cool to older people like me. So in any case, we have the 3 queues, highest, middle, and low, and those are the priorities. Now, what we're going to do to develop our scheduling algorithm is basically just develop a bunch of rules, and we're going to just simply follow those rules. And the rules are pretty simple. We'll do first kind of an approximate, not so great set of rules, and then we will refine them as you discover problems in them. Okay, so pretty simple. So we have our queues. We have a job can be only on one queue, and the highest priority is the high queue, and so forth. So our first rule is going to be pretty simple. It's if the priority of a job, let's call it A, is greater than the priority of B, then A runs, and implicitly B doesn't. Okay, simple rule. If we had this system up here, we can look at it, see A at the top, B and C below it, D below that. If nothing changed about this system, and we only had one CPU to run, which we're assuming for now, what would happen? A would run, just A would run, and A would continue running forever. This would not be a good scheduling policy if we stopped at this point, because just A would run, and B and C and D would all wait there, but that's how we're starting. Okay? Any questions about that? Does it make sense? It's a simple notion, and schedulers often encode how they're going to do things into priorities. They say, this is the most important thing for me to do, that's my highest priority. This is the least important thing for me to do, that's my lowest priority. And then they change them over time in order to meet certain scheduling goals. So let's add to this rule. We have an immediate question. Let's say we didn't have job A here. Then we have a question immediately, which is what? What question comes up if job A didn't exist and we had the queues that look like this? Somebody. Yeah. Does B or C go first? How do we decide between B and C? So all we're going to say there is if the priority, which I'll just indicate with P here, or I guess pri, of A, I'll keep A and B as my jobs, equals the priority of B, two different jobs. Then what we're going to do is we're going to round robin between them. Okay, very simple. And I'm going to add a next rule here. What we need to start doing is we need to start developing a sense of how our priorities going to change. Because if priorities don't change, we don't have a very interesting scheduling system. You just end up at a queue and you stay there, and either you don't run at all, or maybe you round robin, or maybe you run all the time. So we need to start encoding some change into this. And that's going to have a few pieces. First is, where do you start? What's your starting state? And what we're going to do is we're going to start every new process at the highest priority. Okay, simple as that. And kind of related to that then, we need to say, well, how do we get to lower priorities? And what we're going to say there is we're going to say very simply, if the process uses the time slice up at the given priority, then at end of time slice, move down one level of the queue. Okay, and we're going to have to remember these rules a little bit because I won't be able to quite squeeze them onto the screen as well as show a demo, but we'll kind of flip back and forth. First, just take it in. Any questions about these rules? Do they make sense? So we start off at a high priority. If we run to the end of our time slice, after we run, we move down. At any given moment, the scheduler is only going to run whichever queue has one or more jobs in it, and it will either round robin among them or just run the one that exists. So what I'll do now is just show a few examples of this in action. And by that, I mean I will draw a few pictures. So let me go ahead and draw a few pictures here. Q2, Q1, Q0. And this is all pretty simple, right? This is all, stuff that, hopefully that at the end of this you'll have a pretty good sense of how it works. So let's say we just have one job, right? One job is our first example. How is that going to look? Well, let's say it's job A. It starts running. We'll do these diagrams like this, where we have time going from left to right, and then we're just showing what's on the queue at different times. We have our one job, job A. And let's say job A runs for a while, and then at some point an interrupt goes off, and maybe many interrupts have gone off, but the OS is counting. It's counting how long A has been running at level Q2, or the highest priority. And what we will do then is the OS will say, you've run long enough at that highest priority, and what you need to do is move down. So it'll move it down to this level. And it'll start running there. So it runs here, then it gets moved down, runs here. And again, a timer interrupt goes off, and then we run here. And then there's not much to do here other than keep running for however long that we run for. So that's pretty boring. It will get ever so slightly more interesting than that in a moment, but that's a pretty boring what happens. You come in, you're at a high priority, and you just move down to a low priority. So let's look at a little bit more interesting of an example. Let's, example 2. We have a long running job. We'll call that controversial A. And we will call our second job, what should we call it? C. Okay, I like how you people are thinking. Very adventurous. We have a job C, and job C is different than job A. It's a very short running job. In fact, maybe there's a whole bunch of jobs that occasionally come into the system. Job C1 through C2, through whatever. So these come in periodically. A new C class job comes in, and it's just going to run for a very brief period of time. So we have long-running A, and we have C's that come in periodically. So let's go ahead and look at how that's going to appear. Again, we have our Q's, Q2, Q1, Q0. Remember, this is our high priority, this is our low. A comes in first. Let's say it gets moved down, and then it's running. And then at this time, this momentous time, I can't draw a straight line, one of these C jobs show up. What's it going to do? Where's it going to show up? Q2, not too hard. Everybody doesn't want to answer it. So let's call this job C1. And let's say jobs of the C flavor only run for one time slice. So C1 runs. Something happens over there. C1 runs, and then C1's done. Now it's done, and then now done. And then A keeps running. And then, then C2 comes. And of course, C2 then runs immediately because it got entered in the system. It runs immediately, and it also exits really quickly. It's a short-running job. Sounds great. Then A keeps running, and so forth. Now, what's really nice about this system that we've built already? What's a good property of this system? Sorry? Has a quick response to short jobs. Yes, you had a question. Or do you have an answer? Can't hear? Answer. Yeah, perfect. In fact, you can see that it's already discriminating between these two types of processes. Long-running jobs end up here, right? Long-running, end up at a low priority, which mean, yeah, they're running down there, but if something new comes into the system, it's going to get a better chance to run. And as we see here, this works very well in this case because C1 and C2 come into the system, get to run right away, and we get that benefit of a short job getting quick response time. Now, if you're thinking like an adversary, if you're thinking like a bad person, if you're thinking like a person who likes to destroy things, you're going to start seeing problems in this. But there was a question in the back. Great question. So the question, which I could hear, but barely, so it's yell from the back, is what happens if a job that's running doesn't use its whole time slice? So we'll get to that in a second. That's a great question. There was another thought here. Yes?
So what if the time slice is too short, that most of the process is within the highest priority, so that they get to
Right.
run at the lowest?
Yeah, I got you. So the next question, too, is what if the time slice is too short so that basically every process very quickly gets demoted to the bottom? Well, the shorter you make the time slices, what you're going to do is you're essentially turning the scheduling policy into round robin at the lowest priority. So clearly setting the time slice appropriately is going to be something we're worried about. And we'll talk more about setting that a little bit later, too. There was another comment or question or thought or objection or grievance, or you forgot your question, or I'm imagining things. All these are possible in 537, session 1, part 3. Okay, so any questions? Make sense? But now we're getting back to being an evil person, which you should all be excited about. Let's say you had arbitrary, let's say you were a bad person and you wanted to run processes on this system that cause problems. What would you do? Yeah. Spam a whole bunch of short ones. Yeah. Is spam now a generic term for everything bad? Yeah, but it is. So that's exactly what you would do. What happens here if you just run, you create a large number of these. Oh, I'm supposed to make those red. Well, I'm not going to do that. Let's say we create a large number of short jobs. And large means never ending. Every time a short job ends, I create a new one. In fact, I'm pretty clever, so what I've done is I've chopped up my work so that everything I do is just short jobs. What will happen? Clearly what happens to job A is really the question in that case. To A, or what our canonical long-running job. What happens to our long-running job, of course, is if there's an endless stream of short jobs that are being given to the system, we have a bit of a problem. And that problem is something that's all schedulers need to worry about, and I guess you need to worry about too. It's a problem called starvation. You need to worry about it in class when building a scheduler, but you also need to generally worry about it like you need to eat. So you need to worry about this on multiple levels, I guess, multi-level. I don't know where I'm going with that. It's clearly not a... Sometimes you can sense there's like a good sense of like some material that's going to be funny, and then sometimes you go down another path and every word you say you regret. So we'll see both of those, and hopefully in some balance this semester. So in any case, we have starvation is a very general problem with the scheduler because you're deciding who gets to run. And so if you're deciding who gets to run and you're not careful in how you build that policy, of course what's going to happen is you're not careful and you just run one type of job and you forget completely about another type of job. Clearly, this policy, which we described way up here, does something right. It lets short jobs quickly run, and if they're done quickly, we're kind of happy. But it needs to make sure long jobs make progress. So that's a problem. So maybe we'll address that first. So how to ensure long-running jobs make progress. How do we avoid starvation in a scheduler? I don't know, make something up. What would you do? Yeah. Yeah, and there's lots of flavors to do this. The general idea is exactly what you said. The general idea is once in a while, long-running jobs need to move up in priority. If they don't, they're going to face this starvation problem, very fundamentally. So let's make that a rule. And the rule is, there's lots of different, you'll notice this is relatively arbitrary. We're just doing a general set of rules that kind of work, but you could do it a lot of different ways, just like any algorithm that you come up with. So the rule here that we're going to add is that every, say, t seconds, we're actually going to do something very simple. We're just going to move all jobs to the highest priority. You could do it differently. You could move things up more slowly or whatever. But it's kind of simple just to say, we're going to move you back up to the top. So in our example here, A would run for a while and keep getting interrupted by C's. But then after some period T, maybe which is a long period of time, T, A is going to jump back up here. And once we do that, because we know we're going to do round robin at the top level, and maybe we're a little careful how we construct that round robin so jobs don't get stuck in front of us on that round robin queue when they're new and after us, we know that eventually we will run. And when we run, that means we're making progress. We might make slow progress, and we might want to worry about that later, but we know we're making progress, and that's pretty good. So that's a new rule, and we're going to have that property. Now, this rule turns out to have other beneficial side effects. Interesting. So we were trying to solve the starvation problem, but we also added another kind of property to this system. Can we think about what this allows in terms of what does it change about how we learn about jobs? Essentially, before we were just learning once, hey, you ran a little while, now you're a long-running job. What does this allow to happen? Because periodically we're resetting our learning, essentially. What does it allow to happen? Yeah. You get more granular control. Can you expand on that a little bit? What do you mean? I think you're onto the right thing that at least I'm fishing for here. So what do you mean? Oh, you could, yeah, that could be. It's not quite what I'm getting at. That's kind of an interesting idea. Maybe you don't have to do quite as much accounting. Yeah, what do you think?
The nature of the job might change.
Oh, yeah, nature of the job might change, right?
It could be short in the beginning, but then it's a long part.
Yeah, the way to think of that, the nature of the job might change. Um, that's definitely true. You might have a job, for example, a process that takes some user input and wants to be really interactive, and then goes and computes something for a while. And then once it's done computing, it might come back and be interactive again and want to get input again and want to immediately get the CPU and then go off and compute things again and not care for a while. So if the job changes, say, between modes of interactive and what you might call batch style computation. Interactive means I want the CPU right now because I'm expecting maybe the user to do something, and batch means I'm just long running, I need to compute a bunch of stuff in the background. You can imagine this. Let's say you're using a photo editor tool, and you're clicking on some stuff, marking a box. You're going to, the tools these days are crazy, right? I mean, if we think we're worried about news being fake now, in 5 years it's going to be all fake videos created by you all just to make other people whom you don't like angry. This is the future of the world: is computer tools used to make others angry in a very realistic ways. How we schedule that process, which is what we worry about in the OS class, is you're messing around with something for a while, and then you click, do this magical thing, which then paste somebody else's lips talking onto whatever the president's face, whoever the president is at that time, and then it magically computes for a long while, and then produces this video that looks like the president said something that the president didn't say. So that job is interactive for a while, and then magic computing batch in the background. And yes, I will be careful not to talk about politics. If you're worried, if you get worried, I said president even, that's worrisome. I will not go into politics. That would be a bad idea. So in any case, that kind of job is not that uncommon, right? Desktop applications have that flavor. And if you do anything compute intensive, that once you hit go and do the transformation, it doesn't matter if it takes 5 seconds or 8. So that's like a batch computation. But then once you want the mouse to be active again and you want to start playing around with things, you want that to be interactive and responsive, and you want to get CPU time. What our scheduling policy does with this new rule is it essentially allows the scheduler to relearn something about the job periodically. They could say, oh, now it's interactive, and some parts of it get to run again and make sure that things happen. So we get a little bit of a side benefit from that. Okay. So that's our scheduler so far, which is we've just been assuming we're using CPU time. And what we're assuming is that we move down these queues, and that therefore short jobs come in and immediately are serviced. Long-running jobs move to the bottom, but we make sure not to starve long-running jobs by periodically bumping them to the top. All sounds good so far. What we need to now do is we need to worry about one more thing, new worry, which is I/O, which was a question asked earlier. And I/O happens in lots of different ways. Sometimes you're waiting for a keyboard input. Sometimes you're waiting for a disk I/O. Lots of reasons that you might do I/O. And as we talked about last time, if you think about CPU and say a disk or something like that, you're running for a while on the CPU, then you issue an I/O, and then you wait a long time, and then maybe you start running again. And of course, what the scheduler is going to do is it wants to run something else at this point in that gap on the CPU, because then we get the most usage out of our system. That's how we highly utilize a system. It's the core of multi-program systems. We want to switch between things and use as many of the resources as possible in general. So jobs do I/O like this all the time, disk, keyboard, and we'll talk more about that later in the class, how they exactly do that. But we need now to deal with something when a job is in one of our queues and it does one of these I/Os. And we have to be a little careful how we define this. So let's say we have job A, which is our friend, the long-running job. And then we'll do another color. Let's do purple. This will be job B. Job B is the I/O job. I/O job. So A runs first, and A does its usual thing, moving down these queues. And then B comes along. Now B, I guess I should have shown this a little more carefully. A is going to run its kind of full time slice. Let me just erase this first. So we have some notion of our time slice, which we can call, or quantum length, let's call it Q. And A runs its full quantum. A, and then down here too. A, and then A. And then let's move this over here. What we have here is B, but when B runs, it just runs for a little tiny bit of time. And then it issues an I/O. So it's like, does a read, like doing a read. As you know how to count reads now, or you should, or if you have no idea what I'm talking about, this class is not going to go well for you. So, you should know how to count reads, but processes do reads all the time. They read from standard input to get your keyboard input. They read from disk files to get data from the disk. They read from network sockets to get messages over the network, et cetera, et cetera, et cetera. So we have job B here, and B does an I/O. So the question is, what do you do about this? What do you do when B does an I/O and gives up the processor before it needed to? Well, of course, what the scheduler would do is just start running A for a while. At some point, B becomes ready to run again. And then, maybe we'll decide to run B at this point. And it runs for a short period of time and then keeps going. So let's do a naive rule for dealing with this. Naive rule for I/O jobs is if the job, I'll say job instead of you, I won't make you a process. If the job runs for less than, let's say less than the time slice then what we do is we just stay at the same level. As we did here in this example, right? We said B just kind of kept running along, and because B is a nice job, it just gets these little bursts of CPU time. And A keeps running underneath of that and makes a lot of progress because it's a batch job. So that's actually kind of nice. You could almost view each of these little slices of B as these little interactive bursts, which we actually want to run relatively quickly, right? Because it's maybe getting user input and then doing something, then getting user input and then doing something, et cetera, et cetera. Maybe it's just a shell, for example. A shell is a good example of a job that will behave exactly like this because generally the shell isn't doing that much. And you'll learn a lot more about the shell even later tonight about how that works. But this rule isn't called the naive rule for a reason. One is the signal from teacher to student that it's not the good rule. So you should take that as a signal. It's a strong signal. Hint, this is a hint from me to you. But what is the problem here? What is the problem was just you said I gave you 10 milliseconds to run for on the processor. You only ran for 5, therefore I'm just going to keep you at the same level. Yeah. Yeah, exactly. So right there we have what's called a future black hat who's going to hack into systems. And the black hats, what they do is they know how to exploit systems. This has been going on since the day one of computer systems. In fact, it was a bigger deal because there was a mainframe, right? The mainframe was the shared computer system, and it was very hard to get cycles. So what you were trying to do is be devious and figure out how to get more cycles. And the way you did that at first was you studied the scheduler, and you figured out if the scheduler had a little bit of a weakness in it. The weakness of this scheduler is that if we, I'm going to erase this because I don't really want to talk about security right now, but what we're going to do is something called, what people traditionally have called gaming the scheduler. Oh, what am I doing? And gaming the scheduler means, hey, I know that if you 10 millisecond time slice is what I'm allotted, and if I only run 9, I know that very likely I'm going to give up the CPU before you check, and then you're going to keep me at the same CPU. So what B will do, if they're clever, is exactly that. And what that will look like is something like this. B will run for a while, but before the the time slice was going to end right here, but then, A ran for a little bit of a while. But then B became immediately, at the time slice time, became ready to run again because maybe it issued a very short I/O that it knows is going to complete very quickly. And therefore, at the next time slice, instead of A continuing to run, B ran for a long time, but not quite the whole time slice, et cetera, et cetera, et cetera. So we can take over the machine if we're not careful with this very basic, simple-sounding thing of, if you don't use up your time slice, you stay at the same level. So what should this rule be like? What should we do in the OS to prevent somebody from this kind of simple gaming? Yeah. Yeah. What we have to do here is we just have to do essentially better accounting. Accounting sounds boring. As a profession, I don't know, probably is. I guess I don't know anything about accounting. Maybe it's exciting. But OSs do accounting too, and that actually sounds boring as well. But what it means here is just the rule really should be if you use up, if a process, if a job uses up, whatever the quantum is, the quantum, it moves down. It doesn't matter if it uses it up in little slices or in one big slice. We have to account each time it uses the CPU, how much it's used the CPU for, and once you've, at a given level of the queue, if you use up your time slice, maybe in a bunch of little pieces, you're going to move down at the end of that. So you stay at the same level until you use up the entire amount of time that you're allotted. It's very simple. It's kind of, I would say it's obvious, and go forward from there. Okay, just two more things about, really one more thing. Let's talk about multi-level feedback queue, and then we'll take a few questions and take a break. So one thing we didn't talk about, there's some parameters that are important. Important parameters for multi-level feedback queue. So we have our queues, n through 1, or 0, let's say, is what I was saying, or n minus 1 through 0, so we have n queues. So first we have to figure out how many queues we need. That's often like the Solaris scheduler, which is one of these very classic general purpose multi-level feedback queues, allowed you to pick as an administrator how many queues you want based on some sense of how many jobs you want, how long before something became considered a batch job, etc. We have a notion, let's call it Q for the quantum length or the time slice length. And as we talked about earlier, if you make those too short, you kind of make the whole system into a low, everyone goes through the bottom level and becomes just a round-robin system. But it's not only one quantum length. You, in fact, might have a quantum length per queue. And pretty commonly what you'll see is at the top, very short quanta, and then in the middle, kind of longer quanta, and then at the very bottom, even longer quanta. As you know, the job is more and more likely kind of a batch job. You just kind of run it longer before bothering to check, which kind of gets at the granularity comment earlier about how we might have some benefits in the system. That certainly happens as you change the quantum length. And then we had one more parameter that we might care about. What was that? How far back do we have to go? Let's play spin the slides. Oh, too far. This is more fun for me than it is for you, because you're like, it's not fun for me at all. So that must be true. So what's this parameter on this page? Remember this guy? This reset interval, right? How often do we boost jobs up from the bottom up to the top? We called it T. Like I said, that's remarkably fun. What we have is T, which is this reset period or something like that. How often do we have to move jobs up from a low level, say, to the highest level? All of these are configurable. And how you configure them, well, that leads to one of our magic sad points of this class, which is how to configure anything. It's kind of a mystery. Usually what people do is what's the classic approach to this when you install a system and you're the person in charge of it? You use the defaults. So, whenever you're setting, what do you do when you don't know how to build a system exactly? What you do is you say, I don't know how to do this, so I'll make a parameter and the user can pick it. And that's meaning that, you, the expert doesn't know how to solve the problem, but you're hoping that the user, perhaps less of an expert, is going to somehow magically fill in this number. It seems a little bit hopeful. And then, of course, what the user is going to do is most of the time they don't even know this thing is configurable, so they will just use the defaults. And so therefore, whenever you're doing this in a system yourself, please think about what the defaults are, because the defaults will be used more often than probably anything else. These days, probably you would say, oh, I'll do some machine learning because, I don't know, it sounds cool to use machine learning to solve problems like this. So that'll be our modern answer. Old school, how to configure was a mystery, and we use the defaults. The new school, we use machine learning. And we'll use this throughout class. I won't really talk seriously about machine learning at all. But I bet in fact, I bet there's already some research papers on how to do machine learning to set scheduling parameters. And that's not crazy. It's not crazy to run a bunch of different things if you have a known workload and try to have the system figure out what the best parameters are. But you can imagine what these might be. You have some number of queues, I don't know, 3 or 5. The quantum lengths, you make them a little bit longer. You guess at what this is, 10 milliseconds, maybe down here it's 100. And this reset period is, on the order of seconds, so that jobs don't get starved. Okay, so that's our unsatisfactory ending to the multi-level feedback queue, is it's how to configure it. It's not necessarily a known problem, or there's not a known solution. That's great. Okay, so why don't we lean towards break 1. First, I'll do 2 things. First, any questions on this? Yeah. 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 So the question is, can we make the parameters variable, and then maybe the system can learn them over time? Sure. We still have to figure out how to learn what's better and worse. So that's absolutely, you can do that, but we still have to have a method for doing that. And that's something you could view that as a research project. One last thing. So that's any other questions? Yeah. One more question. Yeah, so what I meant just there really quickly is at a given level, like Q2, let's say, my quantum might be something like 10 milliseconds. That's kind of a ballpark that you might think is reasonable at maybe a very high priority. So something that's pretty short. Human reactions, we kind of notice things on the order of hundreds of milliseconds we can notice. If things start to take seconds, we definitely notice. If they take less than 50 milliseconds, it's hard for us to tell how quickly it went. So 10 milliseconds is pretty quick. So if the job is running this whole time and just using the CPU, then it's used up the quantum. It's used all that CPU time is all I mean by that, and then it's going to get demoted. Job B over here, it runs, say, 1 millisecond, and then all it does is it issues an I/O. And when I issue an I/O, I no longer leave the CPU. I just need to wait for that I/O. And if you remember what we looked at before, if you think about a job, it's either running, like the jobs we've been talking about, which means it's on the CPU, or it's blocked waiting on I/O, which means it's issued an I/O, or the I/O is done and it's moved to a ready state, which means it could be on the CPU, but it's not. And then getting to run again is called scheduling, and getting chosen not to run at that point is getting descheduled. So all I'm talking about is, if we're running on the CPU, then we use up, and we just keep running, we're going to use up our quantum. If we issue an I/O, that means we didn't use it up, and it means we have to figure out what to do with those jobs. And so eventually we want to just make sure that anytime we're running over here, we make sure to account for this, so that when you've used up your, say, 10 milliseconds of time at a given queue level, that you move down. Does that make sense? Okay, I gave you too much of an answer for, you probably had that about 10 seconds into my talking. But as I'm told by many people, like my family, I give way too long answers on questions, so you'll have to get used to that. Okay, so now we're going to be at the break. I'm going to give you, since we need to talk about something after break that isn't related to class, we need to start making up topics to talk about, which will get us to talk about something else. Today it's the best sports-themed movie. So discuss, introduce yourself to someone next to you, have a vigorous debate, and then when we come back, I will give you the answer.